Lesson number 2 in chapter 3 is on a concept called correlation. Now, in the first lesson we talked about scatter plots in general, how scatter plots can have direction, form, and strength. Direction was positive or negative, form was linear, curved. We didn't really get into too much besides the linear stuff. And then strength, we could have strong, weak, and then really anywhere in between. What we're going to go off today is, instead of just using adjectives to describe the strength, we're going to be able to tie in an actual number that can help us describe strength. Didn't you see all that? Alright, so a scatter plot displays direction, form, strength, relationship between two quantitative variables. Cannot be categorical at all. Must absolutely be quantitative. Now, again, this chapter and really in this whole class, we're really just going to focus on linear relationships because we're going to use our linear lines to try to make a pattern so we can make some predictions based on numbers that we don't know, that if we did come across a particular x value, we could use a line to be able to predict what a y value would be. And correlation measures the strength and direction of the linear relationship between two quantitative variables. Again, we're going to use this idea of correlation, which will be an actual number. We'll get a number out of it, and the number will help us be able to describe the strength more clearly, whether it's strong or very strong or weak or anywhere in between. And the correlation number will help us be able to distinguish direction, whether it has a positive or negative association to it. And the little part I left out up here, the stronger the linear relationship, the more useful that the data is going to be for making our predictions. Now, if I've got two scatter plots here, and I were to ask you which one had the higher, or which one do you think had a stronger relationship, plot A or plot B? And at first you're probably going to go, well, B, I would say, is stronger than A because all of these points are really close to each other. These look like they're more scattered about. But the thing is this, look at the scales. Okay, notice plot A, this is probably somewhere in the 60s, all the way up to the 130, somewhere in there. And then notice the scale on the X over here. This is again about in the 60s and about in the 130s to 140s. Really, the only thing I did was to take plot A and really shrink it so it looked like plot B. If I took B and kept increasing it, eventually, well, it's kind of hard to tell right now, but it would look more and more like A. Or if I shrunk A really super tiny, it's kind of hard to see. Hopefully you get my point here. One is really the zoomed in version of the other, is the point I'm trying to make here. So the whole moral of the story is, if I can unhide what's being, there we go. Our eyes can be deceived. You really thought maybe B was better than A, but they're actually the same. And we need a numerical number for our strength. And that's what our R is going to represent. Anytime you see R, that is going to stand for our correlation. Now this is a super crazy formula that you will not have to remember. We will never, ever, ever calculate correlation by hand. We'll always let the calculator do it for us. So don't worry about this. It's probably in your formula sheet. I can't remember if it specifically is or not without it right in front of me, but you will never need to know this. Okay? But the correlation uses each individual x value and each individual y value. It uses the mean for your x data and the mean for your y data. It uses standard deviation. Really, what these are individual z-scores, because here's x minus mu over sigma, or x minus your mean over the standard deviation. Each of these represents z-scores for your x values and z-scores for your y values. Adds them all up and then divides them by n minus 1. So in a way, it's kind of like taking an average of the product of all the z-scores. Essentially is what correlation is. Alright, here's where you're going to need your calculator. And I have a picture here. I don't know where it went to. Awesome. Okay. Okay, I found my picture. It was hiding. Anyway, you'll need your calculator. So go into Stat and Edit, and we're going to put these numbers into List 1 and List 2, so clear those out. And the background behind this example is incomplete dinosaur remains were found in an archaeological site, and these are for a particular dinosaur, and they were able to locate the femur and the humerus bones of these dinosaurs, and they found 5 of these dinosaurs. So they are wanting to know, could they use the femur length of the bone to be able to predict the humerus length? So we've got all these. So if a archaeologist came across another incomplete dinosaur, but they only found the femur bone, could they use the length of the femur bone to be able to predict how long the humerus bone is that is just missing? So go ahead and put those into List 1 and List 2. And again, you'll go to second, Stat Plot. Hopefully your scatter plot is still on from yesterday. You'll want to make sure you still have List 1 and List 2 for your X list and Y list. And then when you hit Graph, remember your window is set for the last scatter plot you did. So you'll probably have to hit Zoom 9 for Zoom Stat, and you should get a scatter plot that looks like this. Let's see, I'll just stick it over here. Alright, so is the relationship positive or negative? Well, you can clearly see that this has positive slope to it, so it is positive. And would we call it strong, moderately strong, no correlation, which means there's absolutely nothing there. It's moderately weak or weak. I would probably call this one strong. Some of you might call it fairly strong. Moderately strong would have to be pretty much it's almost making a straight line. Now, what we're going to do next, put this right up here. Yesterday we kind of alluded to if we were to draw a line that would kind of go right in between most of our points here, that this is going to be the linear relationship, this line that we're going to try to put in here, our regression line. Now today, we're not exactly going to talk about the line, but how we can come up with the slope and the y-intercept for this line. So the next thing we're going to do is calculate what those values are for your slope and y-intercept. So for number 3, we're going to go to Stat, press your Stat button, go over to Calc, and then go down to number 8, or you could just press 8 at this point, for ln reg a plus bx. Now for whatever reason in statistics, instead of thinking of y equals mx plus b, we kind of focus on y equals, we just switch it around. We switch around the y-intercept and the slope. Now there is another option where it's ln reg ax plus b, which I think it's somewhere up above 8. But for whatever reason, Stats usually doesn't use that form. I don't know why. I think it's kind of crazy. But we're going to go with more this form, where the y-intercept's first and then the slope. Alright, so then once you select ln reg a plus bx, your calculator is going to look like one of two things. Most of your calculators are probably going to look like this up to this point where it just says ln reg a plus bx. Some of you that have the newer operating systems, or maybe you've upgraded your operating software, you're going to see more that looks like this. Okay. Now, we need to tell the calculator about our two lists that we're going to make our regression line from. So if you notice the little shortcut I've got here, if you press Now this is if you have the old style, this style right here. This is what you're going to do. Press second 1, and then that pops in list 1, then comma, and then second 2, and that'll pop in L2, and then comma. And now we're not really going to focus on this too much for this next part here. It'll come more into play what we're going to do in a day or two. But it's good habit to go ahead and just do it now. But you'll go to the vars button, then go over to the yvars, function, and then you'll select the first one, y1, so it puts it in right here. And really what this is going to do is, once you do the linreg command, it's going to take the equation for the regression line, and if you were to go back up to your y equals button, it'll put the equation of that regression line already in your y1 so that you could graph it. Or if you now went back to your scatter plot, it'll graph that line in there with your scatter plot, so you can see how it should look amongst all your data values up here. Now if you've got the newer software, all you're going to have to do, and usually these are probably already put in there for you, but your X list, you need L1, Y list L2, and then store reg EQ, then that's where you're going to follow along with these steps right here to get that Y1 into place there. And then you'll go down, highlight, calculate, and then it should give you this screen here, which let me bring it up to the top layer. This is what you all should see. You should see y equals a plus bx. Here is your y-intercept. This is where the graph touches the y-axis at negative 3.69 or 65, etc. Here's your slope, the b, the 1.1969, etc. Now, if you don't see an r and r square value here, which most of yours probably won't have it, this is what you need to do down here at the bottom. You need to press second 0 to go to your catalog. Scroll down and find the command Diagnostic on. Press enter so that it goes to your home screen. Press enter again and it'll say done. Now if you go back, or really shortcut command would just be to press second enter and keep pressing that until you get this command to come back, your linreg, and then press enter, and then you should have your r and r squared values here. Now r is our correlation value, and you can see that this is very close to 1. It's positive, and actually I think the next page will actually get into that. The r squared value here is something we will talk about in a couple days. And r and r squared are related. R squared is the actual squared version of r, but they kind of represent two different things. You'd think they would be pretty close in their meanings, but not quite. All right, interpreting correlation. When there is a positive association between our variables, the value of r will be positive. It'll be greater than 0 but less than 1, or equal to 1. An example of two variables that are positively associated. One example I could think of would be where x represents age, and we'll say from birth to age 18, and your y-axis, your y variables will be height. Now as you get older and older till you reach the age of 18, your height should be increasing. It's not like you're Benjamin Button, and as you get older you're turning more into a baby, so Benjamin Button would be a negative association. But that would be one example for a positive association. When there's a negative association, then r will be negative. So we can flip things around like this. So it could be equal to -1, but not equal to 0. And an example of two variables that are negatively associated, you could think of maybe your x-axis represents miles driven in your car, and the y-axis, let's say, represents amount of gas in tank. So the more and more miles you drive, the amount of gas starts to come down. Because if you think about, you start out with a full tank of gas up here and you haven't driven anything, but the longer and longer you drive, the gas in your tank's going to be coming down until you hit a point where you're out of gas, and it's the longest you've driven at that point. Correlation makes no distinction between explanatory and response variables. Okay, so in those last two examples I just gave with miles driven and amount of gas in your tank, if I switch those around and said I want the x-axis to be the amount of gas in my tank and I want the y-axis to be miles driven, if I switched them around, like if I did ln reg L1, L2, versus if I switched it around and I said, you know what, I want L2 to be my x values and L1 to be my y values, you will get the same r value. Now your slope and your y-intercepts will be different, but r and r squared will stay the same. Correlation requires that both variables be quantitative again. We need numbers to put into our list. There's no way that you could put categorical values into your list. You could type them in there, but it will probably give you some sort of error. Correlation has no units of measurement. So if we were talking about, again, our miles driven, which is obviously in units of miles, and amount of gas in your tank, which would be probably in gallons, when you do correlation on that, whatever value you get for that has absolutely no unit. It's not miles gallons or gallons miles, it's just that number, nothing else. Now, we've mentioned before, correlation is between -1 and 1. And here's some examples. This isn't set in stone or anything, but at -1, you'd have a perfect negative line. And all the way at +1, you'd have a perfect positive line. All of your data would line up perfectly to make a straight line. Now, if we're at, say, the 0.9 in the negative side, I would call anything between -1 and -0.9 strong or moderately strong, for example. Once you get to maybe 0.9 and start hitting below, then maybe you could start saying strong or somewhat strong, fairly strong, but not as, no pun intended, but not as strong of adjectives to describe the degree of strong. And we could say the same thing down here for the positive. But anywhere in between, it's really a guessing game as to what adjectives you want to throw in there. You could say, I don't really know. I've seen somewhat, I've seen really somewhat, fairly, pretty strong, moderately strong, just saying strong. Those are the main adjectives that I've seen over the years to be able to describe the degree of the strength in a correlation. When you hit about the quarter mark in either direction, here's where you start getting into the weak category. And if it's 0 or pretty close to 0, there is no association. That means all your points are should be just about a circle, that you really couldn't draw a line in there one way or the other, and it makes more sense than any other line you could draw. For 7, correlation can only measure the strength of linear relationships. It cannot determine the strength of curved relationships. So we'll look at some examples down the road where maybe we have something that looks like it's a perfectly curved relationship, and when you go to calculate the correlation value, you're probably going to get something really close or exactly to 0, because all of these data points do not make a straight line. So expect a very low, by low I mean close to 0, correlation value out of that. Correlation is greatly affected by outliers, therefore it is non-resistant, like the mean. If you remember, if I jump back here, to the actual formula, you can see the mean is a part of the formula for correlation. So if the mean is not resistant, well, now therefore correlation is not resistant. Now let's flip back. And if we were to add and subtract the same number for each x or y value, the correlation would not change. Just like the standard deviation wouldn't change if you added or subtracted the same number for all your values. Okay, so correlation in that way is just like standard deviation, just like your measures of spread.